Welcome back. In this video, we will talk about this problem called trailing zeros in a factorial. So what do I mean by trailing zeros in a factorial? Let's take the example of this input 5. So which means we will first calculate the factorial of 5. Factorial of 5 is nothing but 5 times 4 times 3 times 2 times 1, which gives 120. And if you see in this 120 as a trailing zero, which is zeros at the end, we have one trailing zero, and hence the output is 1. In a similar way, for the input 10, we will have two trailing zeros, and for the input 4, there are no zeros, right? Because 4 factorial is 4 times 3 times 2 times 1, 24. It doesn't have any zeros, so hence the output is 0. And for input 100, we have output as 24. So it has 24 trailing zeros. Got it? Now that we know what we need to calculate, let's look at a naive solution first. So I have opened the code. So let me create a new file. So 04 trailing zeros. Okay, trailing zeros.js. So let's create a function trailing zeros, and this takes the num as an input. And now what we need to do first, as I said, first we need to calculate the factorial. So let fact for factorial is equal to, let's copy this factorial function from the older code which we wrote in the previous lectures. So I'm gonna rename it to just factorial, and now we have this function to calculate the factorial, right? So let's just call factorial of num. So now that we have calculated the factorial, let's calculate the trailing zeros. So for that, first let me initialize the result variable to 0. And after that, what we will do is like while fact modulus 10 is equal to 0. So until the fact modulus 10 is equal to 0, we will do result plus plus, and then fact is equal to math dot floor of fact divided by 10. The same logic what we did for counting the digits. What we are basically doing is like, now we have this factorial of a number, and now we check whether this factorial is modulus, when we do a factorial modulus 10, whether the remainder is 0. If that is the case, then we know we have a trailing 0. So we add to this result plus plus, and then we remove the last digit, which we do by math.floor of fact by 10. Again, it will check for fact modulus 10 whether it is equal to 0. If it's not the case, then it will come out of that loop. So at the end, what we need to do, we just need to return the result. So let's try to add some test cases. So console.log trailing zeros of 4. Okay, let's add couple more. We know for 4 there is 0, and let's add it for 5 as well. Okay, and if you remember, yeah, for 5 there should be 1, and for 10 there should be 2, right? So let's add 10 as well. Great. Now let's try running this program. So node 04 trailing zeros.js. You see, we get the right output. Trailing zeros of 4 is 0, trailing zeros of 5 is 1, and trailing zeros of 10 is 2. Okay, Harish, but you usually give me an exercise. Why didn't you give me an exercise? The reason being that there is a big problem with this approach, and hence I would like you to think of a better approach. Before that, let me explain what is the problem with this approach. So if you remember, when we pass the number as 100, we are expecting the output to be 24, right? Let's see what happens. So I have console.log, so 100, and now if you try to run, it says 0. That's interesting. What's going on? This is actually due to a problem called integer overflow. So basically a number can hold on until only it can hold only until a certain value, beyond which it is too much, right? And basically here what's happening is like, if you check out, maybe I can run it and let's see what is the factorial value. So console.log of fact for trailing zeros of 100. Okay, you see it says 1.93 to some digits e power plus 157. So it does give some kind of approximate notation, but ideally what happens is like, this doesn't take into account of trailing zeros, hence we have this issue. So what I'm trying to say is like, this issue is caused by some kind of integer overflows. So because it couldn't hold that kind of number, hence this program is not suitable for very large numbers. Okay, so how do we solve now then? Okay, here's where we make use of some interesting facts about this factorials. Let's see what those are about. Okay, so let's see what 5 factorial is. We know 5 factorial is 1 times 2 times 3 times 4 times 5, which is equal to 120. And one interesting fact about this factorial is that, when do we get 10? If you multiply 2 and 5, correct? Now if you see here, there is 1 2 and there is 1 5 and there is one trailing 0. Can you correlate now? So basically what is a correlation is that, if you can find the number of 2s and 5s, then we know number of trailing zeros. This is the correlation. So here we have 1 2 and 1 5, and hence there is one trailing 0. If there are multiple 2s and 5s, or let's say like there are like 3 2s and there are 3 5s, then we know there are 3 trailing zeros. This is the fact that we are trying to use. But we can even simplify more, because in the factorial, 5 always occurs less than 2, right? Because it's the smaller one. So 5 is always the limiting factor. So you just need to take account of 5. That's all. Nothing else. But you need to be wary of one thing. For example, in the case of 5 factorial, if you see it's 120, so we say there is 1 5, correct? But what is the case for, let's assume we are calculating something like 25 factorial, okay? So it goes from 1 into 2 into 3 into 4 into 5 into ... till 25, correct? But now we also know that 5 occurs during, like something like 5, 10, 15, right? But then when it comes to 25, right, it is actually 5 into 5. That's interesting. So here, if you divide it by n, if you divide the n by 5, we have calculated the number of 5s, okay? But then when you compare this 25, it also has one additional 5. So what we do, we again do a n divided by 25. And then if the number is still greater, for example, let's take the case of 251, okay? What we will do is like, we will do 251 divided by 5. Great, we will get the number of 5s. And then we will also see, we will do 5 into 5, which is 25, right? 25 is still lesser than 251. So we will divide 251 divided by 25. Now we will get the extra 5s which were missed out. But next case, again multiplied by 5. 125, if you see, it contains 3 5s. So now what we will do is like, 125 is still smaller than 251. So 251 divided by 125, and then we will take a floor out of it. Now if you multiply 125 by 5, it is definitely bigger than 251. So we get the summation of n by 5 plus n by 25 plus n by 125. So we do this loop until this, whatever this factor of 5 is, greater than the number, whatever is passed. So what is the big advantage of this approach? We don't even calculate the factorial, but we still get the number of 5s, and hence we know how many trailing zeros are present. Okay, so now that you have this idea, try to solve it in the coding exercise using this idea. because the older idea will not work for higher inputs. Okay, so try to solve using this idea whatever I have said now, and let's meet in the solution video. Thank you. Welcome to this solution video. In this video, let's see how to make use of the facts of the factorial which we saw in the last video and solve this problem. Great. So now for the purpose of reference, let me comment this out, and let me uncomment these test cases. So we will create a new function called trailing zeros, which takes num as an input. Okay, now we have the empty function. Now what we will do is, like as usual, we will create the result variable and initialize it to 0. Now we will loop. So now what's the condition is that for let I is equal to 5. So we are starting with 5. Okay, until I is less than or equal to num. And now here is the important condition. What we will do is, like we will not just do I plus plus, but whereas we will do I is equal to I multiplied by 5. Okay, and now inside this what we will do is we will do result plus equal to math dot floor of num divided by I, and at the end we will just return result. To be frank, that's all the solution is about. Before explaining in detail, let's try to run this program. You see, as per the expectation, we should get for input of 100, we should get 24 trailing zeros. For 100, we have this 24 trailing zeros now. It seems like the solution is working, and this solution will work even for big numbers. So what is happening? As I said, basically we are trying to divide it by multiples of 5s. So initially we are starting with 5 and we are going till until equal to number, and for each iteration we are multiplying it by 5, which means at first we do a math dot floor of num divided by I and get the multiples of 5, and then when we do divided and then we multiply I by 5, right, which means now I becomes 25. Now when we do by 25, we will get the extra missed out 5s, because 25 has power of 2, right? So we are missing 1 5, so we also gotten that into account, and now again it will multiply by 5, which means now I becomes 125. 125 is like 5 into 5 into 5. We have calculated 5 into 5, but we are missing 3 5s in a row. So that's why we make use of this method floor of num divided by 125. So this keeps on running until the power of 5 becomes less than or equal to or greater than num. Okay, that's what is happening. So this is the solution behind this. But then what is the time complexity of this approach? Basically what we are doing is, like we are doing something like 5 power k times, right, which is like 5 into 5 into 5 until it has become less than or equal to n. This is very much, if you take the very much equivalent to when we take a log, something like log base 5n, and hence we say the time complexity of this approach is big O of log n, and the space complexity, we don't have nothing much apart from this result, so the space complexity is big O of 1. Okay, so I hope you understood the problem. To recap, basically when we do 5, right, 5 where and all it comes at 5, 10, 15, 20, 25, correct? So now whenever we divide it by 5, we will get the number of 5s. But the problem is, if you see the 25, it also has one more 5. We only calculated 1 5. That's why we divide again by 25 to calculate the left out 5s. Same thing for 125. I hope you got this logic. So that's it about this trailing zeros. See you in the next one.